Hello and welcome to our lecture on the center of mass. Okay, so we should, in our discussion of the center of mass, first of all define what it is. Okay, and it's basically what you think it is based on the name. Okay, so the center of mass is a point where the mass is at its center. It's a balance point. Okay, so it's a balance point of the mass distribution. So in this case, we would have the mass of the handle on one side of the center of mass and the mass of the head, and if this is, like a hammer here, on the other side. And the center of mass would be closer to the head of the hammer because there's more mass over there, okay? So the balance point isn't always in the middle if the mass isn't evenly distributed, okay? But that's the balance point, all right? It is a point of an object that follows the path of a particle. So if I was to throw this hammer and have it take a projectile trajectory, the center of mass would follow the path that a particle would take. It's almost like if we reduce the hammer to a single particle. Now here's the thing, what about the rest of the hammer? Well, the rest of the hammer, if it is given some initial rotation, would rotate around that point. And so if you watched it, it would be kind of a funny rotation, right? Because the head would make tight circles, and then the tip of the handle would make larger circles, okay? But it would rotate about the fixed point because the center of mass would not rotate. It would follow a entirely translational path, okay? So that's an important idea about what the center of mass represents. And it's a good tie-in between thinking about objects and rotational systems and comparing them to, well, translational systems. And we'll talk more about rotational systems later, okay? Also, it is the only point of an object where the gravitational force vector is applied, okay? This will become very relevant when we define gravitational torque, okay? But for now, we're kind of thinking about center of mass in the context of momentum, okay? But mostly it's its own topic, although we'll tie it in with momentum, you'll see that, okay? But here's an important idea that's going to become more applicable. I will certainly remind you when it comes up, okay? But it is the only point where gravity is applied, okay? And of course, for a particle, gravity only acts at the single point because a particle is a single point. But this hammer here is not a particle, is it? So it has a center, and it's got mass around that center. Now here's the thing. Note, a common misconception that I want to clear up. The center of mass does not necessarily have equal mass to each side of it. So yeah, it's the center of mass, but that doesn't mean that there's equal mass to either side. That's not what it means, because it couldn't be the balance point if that's the case. And you would say, well, but isn't that what it means? Well, no, because think about this picture right here, the hammer. It's a lovely illustration of a system where you cannot have equal mass on either side, because the handle here is lighter. It's definitely lighter than the head, okay? And you might be like, well, that's accounted for the fact that the center of mass is closer to the heavier bit. Well, even then, there's more mass over here. This is a greater mass than the entire mass of the handle, okay? Even though we've included almost the entire handle, it still doesn't compensate. The reason that it's the center of mass is here is not because the handle is equal mass as the hammer, but because the distance of the handle makes the mass at the end matter more, okay? Because the center of mass isn't just the mass, it's where the mass is located. And if mass is further away, it will affect that balance point more. Think a seesaw. Think about a lever, okay? All right, that's the idea. That's the implied idea of the center of mass, okay? Well, now let's get into how we would calculate it, all right? So there's two approaches depending on if we're talking about like a group of particles and thinking about the center of mass of those group of particles, which is called a discrete system because they're discrete chunks, or if we think about a continuous object like the handle. Those would be the two types of center of mass. And then we're also going to relate the center of mass to momentum. Okay, so first of all, this is how we calculate the center of mass for a system of discrete particles. X-com represents the x-coordinate of the center of mass, is 1 over the total mass of the system, so okay, and then multiplied by the sum of each mass element times its position. So essentially, it's the sum of the products of M1 and X1, all right? Or Mi and Xi, really, right? And we're going to be summing up, however many there are. If n equals 5, that means there's 5 discrete particles. And we do the first one, the second one, the third one, the fourth one, the fifth one, right? And each one would just be like this, M1, X1 plus M2, X2, and so on, okay? So total mass, big M, summation, that's a summation symbol. And then this is the x location of the ith particle, and then this is the mass of the ith particle, okay? And there could be any number, usually only like 3 or 4, and that's how we would do our system of discrete particles. And then if we wanted to find the y-coordinate of the center of mass, it's the same exact approach. And if there was a 3-dimensional problem, then it would be the same for z, okay? And then, no surprise, if you wanted to find a vector pointing from the origin, because there's an implied origin here, because all the particles have a coordinate, right? So you have to set an origin, otherwise it makes no sense. And so then you can find a displacement vector from the origin to the center of mass, which would be your rcom vector. And that would just be each of the coordinates of the center of mass multiplied by appropriate unit vectors, I hat, j hat, and k hat, respectively. Okay? So that's the approach. We'll put in the practice in just a moment. But what about if it's a continuous object? Well, then our summation becomes a integral. And that's a key idea in calculus, right? That, as you start summing up smaller and smaller bits, eventually you're summing up things that are infinitesimally small, and now you have a continuous summation, which is an integral. Okay? All right, so this is our continuous solid object. In that case, xcom is 1 over the total mass, but instead of the sums of x and, so discrete masses and discrete locations, it's x and then a actual differential, which is called the mass element. Okay? So dm is the mass element, and it's an infinitesimally small piece of mass. Okay? And the idea then is that x would have to have some functional dependence, right? Or even more, dm is functionally dependent on x is what ends up happening. So there's always going to be a substitution of differentials every time, and that's you have to see it in practice for really have it make sense. But we're always going to substitute out dm because you can't integrate over dm. What would that look like? I mean, it's a great concept, but in practice you can't do it because we need a function, right? And we need the mass to be a function of x. And then we would replace dm with whatever function there is, include the x in our appropriate antiderivatives, and then set our limits of integration. And that's the actual process. Okay. Here's the idea, but we'll put it into practice in one of our examples, or 2 of our examples. Okay. All right. So that's for continuous objects. Now the same thing applies for y and z. Okay, just like it did for discrete systems. And the last idea is this. This is the velocity of the center of mass, v-com. All right. And the velocity of the center of mass is interesting, because it's the total momentum of the system divided by the total mass, okay? And the idea there is that if the momentum doesn't change, right, so if the total momentum remains constant, then the velocity of the center of mass must remain constant, which is basically just a conservation momentum idea. But it's really nice because it tells us the center of a system, if there's no external forces on that system, because that would be when momentum is conserved, the center of that system must remain fixed. The individual parts of that system can move around, but the center can't unless there's an external force. All right, so it's a nice tie-in, and on the one hand, it's something we could have done with conservation of momentum. We don't need really this definition, and it's something we could have done with Newton's third law, for that matter, right? So it's just a restatement, a helpful way of thinking about particular systems. It's okay to be repetitive if we have new tools in our tool belt. The velocity of the center mass of a two-body system, and two-body isn't, it doesn't have to be 2 bodies. This is the example that I wrote here in the formula. I could have been more general and left this as p final and just wrote m total down here instead of m1 plus m2. But I stuck to 2 bodies. Okay? All right, so there's going to be 3 types of problems that we're going to see in the practice. All right? Type 1, problems that involve finding the center of mass for a system of discrete particles. Type 2, problems that involve finding the velocity of the center of mass of a system, or using a known center of mass velocity to find displacement of individual objects. Like, what if we know v and we want to find the momentums, essentially? All right? Even if they're not changing, we can still find individual ones. Maybe we know one of the velocities, but you'll see. All right, and then finally, type 3, the part that involves calculus, complex problems that involve finding the center of mass of a solid object. Okay. All right. So let's start with a simple case. All right. So we're going to start with an interesting one too, a water molecule, H2O. Okay. So the idea is a simple model of a water molecule has the oxygen-hydrogen separation at a distance of 9.57 times 10 to the negative 11 meters. So just under 1 angstrom, and that's this distance here, 1d. Okay. Each hydrogen atom has a mass of 1 atomic mass unit, and this is how many kilograms is in a atomic mass unit. Okay, and the oxygen molecule has a mass of 16 atomic mass units. But we're going to convert those over to kilograms. But actually, we'll just kind of look at the ratio because we don't really, we don't exactly need to convert them over to kilograms. But this distance is relevant unless we wanted the fraction of that distance. But we're going to give it in meters, so we're going to actually use this value. Okay. And then we want to find the position. That means we need the x and the y, okay? So this is where it is, by the way. This is where we find the numerical value. And this makes sense that the center of mass should be located right here, because think about it. It's symmetric about the x-axis. So the y center we should expect to be right at y equals 0, right along the x-axis, because there's symmetry, right? It's already balanced, okay? And as far as the x-coordinate of the center of mass, well, it should get pulled slightly towards the 2 hydrogen atoms here, but only a little bit because the oxygen is much more massive. The oxygen is at the origin, kind of pulling the center back towards it, but it's not quite at the center. It's kind of like considering the center of mass of the sun and Jupiter. the center of mass of the Sun-Jupiter system is still inside of the sun, but it's actually pretty near the surface of the sun because the effect of Jupiter does pull that center slightly out, okay? But it's pretty slight, because the mass difference is huge. The sun is so much more massive. In this case, it's not like the oxygen is many orders of magnitude more massive, but it is 16 times more massive, or I guess eight times more massive than the sum of the two hydrogen atoms. But let's go ahead and do it. All right, so this is the formula. This is just using the summation symbol, but doing it for 3 objects, okay? Because there's a total of 3 objects. There are 1 oxygen and 2 hydrogens, okay? And then we'll plug in our numbers. Okay, so we plug in the 16U for the oxygen, multiply it by 0, so it actually does nothing in the numerator because it is located at the origin. And we could put the origin anywhere, but I might as well put it at the center of the heaviest thing. And then we've got our 2 masses for the hydrogens. I go ahead and factor out because M2 equals M3, so I factor them over. And then actually, even more than just factoring, I just say they're identical, right? So I just combine these 2 like terms. That's where the 2 comes from. And then they each have a mass of 1 U, okay? Notice I left things in U's because the U's are going to cancel. And then I've got cosine of 52.5. Where's that coming from? Well, this angle right here is 52.5 because it's half of the angular separation of 105, because I'm just making a triangle here with this being the x-coordinate and that being the y-coordinate. But of course, it's a much smaller triangle, right? Okay, and that's it, okay? And then it's just, it's just d times that, okay? And there we go. And then we're dividing by the total mass, which is 18, because it's just 16 plus 1 plus 1. All right, and so we plug in all our numbers. For some reason, I actually didn't cancel out the u's already. I went ahead and wrote them out and then canceled them, but you get the idea. Okay, there we go. And obviously this was 0, which is why it doesn't show up. And there is our value, 6.5 times 10 to the negative 12, right? So about 10 times smaller than the distance d, because it's much closer to the center of the oxygen than to the hydrogens. And for y, we should expect it to be 0, but let's go ahead and show that it's going to be 0. So for y com, I'm going to show it's being 0 by just writing it out and noticing that everything cancels in the numerator, right? Because we got the 16 times 0, because the y-coordinate is also 0. It's x equals 0 and y equals 0 for the oxygen molecule. And then these two have negative 52.5 and positive 52.5. And sign of a negative is a negative, which means these 2 terms cancel, because this one would have a negative out in front, which cancels with the 3rd term. And then dividing by the 18u doesn't matter because 0 divided by 18 is just 0. There we go. Okay. All right, let's do it again for a system of 3 particles that isn't applicable to some real-life system like an H2O molecule. It's just some particles, M1, M2, and M3. All right, so shown as a system of those 3 particles, I give you the masses 12.65 kilograms, 9.44 kilograms, and 19.15 kilograms. The displacements for M1 and M2 relative to the origins are both 3.334 meters. All right, so that means that R1 and R2 are going to be, so this one and this one are each 3.334. R3, which is this longer vector here, is just a little bit longer. It's 4.008 meters. The angle of R3 that R3 makes with the negative x-axis, so that's the angle theta as shown, is 28.79 degrees. All right, so let's go ahead and do it. We're just going to consider the coordinates and then balance everything out. Very, very straightforward approach. Here I'm just actually showing the magnitudes as stated in the words of the problem. I include the values of the masses as well, so you can kind of see it all, which is obviously helpful. All right, there's that angle given. All right, and then the right triangle I end up making isn't the one for the angle theta, but instead is kind of relevant to this angle. But it doesn't matter, right? I could have moved these vectors. All right, and this is R3y and then R3x. All right, obviously R3y has to be negative, and then you'll see that will turn out that the center mass is right about there. So it's going to be in the 3rd quadrant. It's going to have a small negative y value and a small negative x value. And then we're going to find out, we're asked in part B, what angle does the RCM vector, which would be this little vector here, what angle does it make with the positive y-axis, which would be, I'm going to go ahead and find what I call the angle beta, which is the angle that it makes with the negative x-axis, which is just like theta makes with that axis. Well, different angle, but the same, relative to the same axis. And then when I go ahead and find phi, I'm just going to add 90 degrees. So that's where you see that beta is just, or rather phi is only beta plus 90. Okay, let's go ahead and go through the steps. Okay, so XCM, 3 particles. All right, one of them is going to be 0 because I'm going to have the M1, or for X it's going to be M2. So the X coordinate of M2 is 0, right, because it's right along the Y-axis. Okay, so M2 just disappears in the numerator. The total mass is going to have M2 included, okay? And there we have all of our particles. Looks nice. All right, and we're going to do the same thing for Y. Okay, and there we have all our values. Okay, I'm just plugging them in. And for Y, notice M1 goes to 0 because obviously this one has no non-zero Y value because it's right along the x-axis. M1 is right on the x-axis. Okay, And then I'm going to go ahead and get the numbers, which I guess I didn't write in here, but here they are. So XCM ends up being negative 0.607, all right, and that just comes from this, okay? And it's negative because this term is bigger in the numerator, so it pulls it slightly in the negative direction. And then YCM is even a smaller value. It's negative 0.133, all right? And so that one's going to be kind of just below the y-axis, okay? If I want to find the magnitude of r, because that's what I asked for, then it's just going to be, using the Pythagorean theorem, we just get 0.614. So that's the length of that vector right there. Okay, good. On to B. Okay, for B, it's definitely always easier to find. Whenever you're finding an angle that's over 90 degrees, I would never recommend not trying to find it. Instead, just find some angle that is less than 90 degrees. In this case, the angle beta, and then add. For example, if I had been asked for the angle relative to the positive x-axis, I would still just find beta, and then I'd add 180. All right. But in this case, since I was asked for the angle relative to the positive y-axis, I only have to add 90. Okay. So never find. Use this idea. Use inverse tangent, but use it when it's appropriate. Okay. And so inverse tangent is going to be YCM over XCM. Why YCM? If we zoom in, well, this is the opposite side. That's the Y component of the center of mass. Because remember that after all, this is R com. And then the adjacent component is X. So then opposite over adjacent, which is the definition of tangent, is going to be Y over X. All right. And then we just plug in the numerical values that we got from our handy dandy formula here. All right. And we get 12.14 degrees, which means that phi is just going to be 12.14 plus 90, or 102.4. All right. Okay. So we got a concept question. Pretty straightforward one. A machinist starts with 3 identical square plates, but cuts one corner from one of them, 2 corners from the second, and 3 from the third. Rank the 3 plates according to the x coordinates of the center of mass from the smallest to the largest. Okay? Because the idea here is that as we cut off corners, that's in effect where the center mass goes, right? So if I remove some mass over here, that means that the x center of mass is going to get pulled in this direction, right? Well, then if I remove even more mass, that means that the x center mass is going to get moved even more. But over here, now I actually remove mass from the positive side, so that means that the x center mass is going to move back a little bit over there. And in fact, if you think about it, in these two cases here are identical, because in this case, these two pieces effectively cancel out in terms of their effect on the x center mass, don't they? Right? Now, of course, they're not going to cancel out. Actually, they're going to cancel out in both cases. They're going to cancel out in terms of the y center mass and the x center mass. So it's almost like they're completely canceling each other out. So the only thing that matters is going to be this one, which is going to pull the x a little bit over here, but just as much as case 1. So in other words, case 1 and case 3 are tied, and then case 2 is going to be the largest, because case 2 is going to have the largest positive value of the x center mass. So ranking from smallest to largest would be 1 equals 3, and then 2 being the biggest. Because again, this one would have the largest x value of the center mass. Okay, because it's got the least mass over there in the negative x values. Okay? All right, now let's do a system that has the velocity of the center mass. Pretty straightforward, but it's good to put into practice. At the same instant that a 0.5 kilograms, or half kilogram balls drop from 25 meters above Earth, a second ball with a mass of quarter kilogram is thrown straight up from the Earth's surface with an initial speed of 15 meters per second. They move along nearby lines and pass without colliding. At the end of 2 seconds, what is the height above the Earth's surface of the center mass of the 2-ball system, and what is the velocity of the center mass of the system? We're going to use kinematics to do our intermediate steps here. All right, here's the picture. All right, and this is the picture, by the way, at the point that matters, which is the 2-second point. Is that everything's regarding that 2-second point. Because interestingly, at 2 seconds, look what's happened. At 2 seconds, A has been falling for a while, right? Because it started 25 meters above the Earth. It's been falling. It's picked up a good amount of speed. It's pretty near the ground. The one that started at the ground and was thrown up with 15 meters per second has already reached its maximum height and is on its way back down. So at 2 seconds, they're both traveling down. B is above A. They already pass each other, and B is on its way back down. Okay? And you can figure that out with just kinematics. But also, it doesn't exactly matter. It's just helpful for drawing the picture. So at 2 seconds, I'm going to go ahead and find their vertical coordinates just using kinematics. Okay, this one has an initial height but no initial velocity, and so then we just use that. B has no initial height, but it does have initial velocity, right? And they both are affected by gravity the same. All right, I'm plugging 2 seconds for both. And so that means for A, we get a value of 5.4, and for B, we get 10.4. Because again, as I pointed out, B is above A at 2 seconds. Okay. All right, so then x center of mass is simply a matter of plugging in their current, values, because it's a one-dimensional problem. So there is no, I guess it's the y center of mass or the h center of mass, because it's completely one-dimensional. There's no side-to-side motion. Okay, and so here we go. We got 5.4 times 0.5, 10.4 times 0.25, and then divided by the total mass of 0.75, which gives us a value of 7.07. Okay, and again, remember that this one, this one's at 10, so this is about 10, and this is about 4, and so 7's kind of halfway in the middle. Not exactly halfway in the middle, because they're not equal mass. Okay, so it's pulled closer to the heavier one, which is A. All right, and then as far as finding the velocity of the center of mass, we simply want to find their total momentums and then divide by the total mass. And so then I find the velocity of A, which is negative 19.6. That's that one, because remember it's been speeding up ever since it got dropped from 25 meters. And the velocity of B is a much smaller value, negative 4.6, because as I stated, it already went to the top. It's kind of near the top, and it's just kind of on its way back down. Okay? And so then as far as finding the velocity of the center mass, it's simply a matter of plugging in the mass times the velocity plus the mass times the velocity divided by the total mass. And of course, it's going to give us a negative value, and it's negative 14.6 meters per second. Okay, now this is a center of mass that is constantly changing. All right, so the velocity of the center of mass of this system is always changing. This is not a isolated system. This is not a system where momentum is conserved because there's an external force. There's gravity. Okay, so this is great. This is good. We can find this as interesting thing to find, the velocity of the center of mass. But it's not like helpful. It's not. It's just not something we'd find in its own right, because it's not a conserved system where knowing the velocity of the center of mass can help us solve for something more easily. But however, in the next example, example 4, this is a system with no external forces. Therefore, finding the velocity of the center of mass kind of knowing what it is, stating what it is, arguing what it is, allows us to solve for other bits of information quite easily. All right, how so? Well, here's the idea. A ball with a mass of 1.82 kilograms rests on a frictionless ramp with a slope of 42 degrees and a mass of 4.37 kilograms. That's the mass of the ramp. This is a movable ramp. The ball is positioned directly above the center mass of the ramp. As shown in the picture, we have to assume that the ramp gets more dense down here in the corner. We'll talk about variable density in just a second. But it doesn't matter. What matters is that we know it's above the center of mass. If the ball is released from a height of 27 centimeters, how far will the ramp slide along the frictionless ramp, or along the frictionless ground? All right, because the ball is going to go this way, the ramp's going to get pushed back that way. All right, we know that's the case because of Newton's third law. We know that's the case because of conservation of momentum, and we're going to be able to easily solve it with the velocity of center of mass approach here. Okay, so since there's no external forces, the velocity of the center of mass must be 0. V com equals 0, which tells us then that 0 equals the sum of the two momentums, the sum of little m and big M, in terms of and their momentums, over the sum of just little m and big M. All right. And so then we're going to go ahead and replace the momentums as mass times velocity. Now this is an accelerating system. They will accelerate. But if I just look at their average velocities, then I can relate that to displacement, which is going to allow me to answer the question, which is nice. It's a nice use of average velocity. Okay? And so then I'm just going to rewrite this as, and then I'm going to multiply both sides by m plus m. 0 times m plus m is just 0, so the denominator just goes away. And so I'm left with the numerator equals 0, and I'm going to replace both the average velocities with just displacement over time. The times are the same, obviously, and so then I just have two displacements, x for little m, the ball, and x for big M, the ramp. All right, and that tells me that x big M for the ramp just is going to be negative the mass of the ball times the displacement of the ball over the mass of the ramp. And then I'm going to replace the displacement of xm, that is, displacement of the ball, with h over tangent theta. Where am I getting that from? Well, I was given the height, but I wasn't given the actual distance. But I can easily find the distance by just cross-multiplying by tangent theta, and that just gives me that xm equals h over tangent theta. All right, so I go ahead and put that in for xm, and I just plug in my numbers and get my answer. And this is a really simple approach to something that you could do in a much more complicated way, because you could set up a free body diagram for both objects, find out that the component of the normal force that pushes the ramp is going to be something like, the acceleration of the ramp, that is, the ramp is going to be proportional to cosine theta, sine theta, maybe little mg, something along those lines, and then I think divided by big M. And so when and that's a pretty complicated free body diagram, takes a lot of steps, and then you could find the acceleration of the ramp. Then you could find out how long it takes the ball to slide down the ramp, finding its component of acceleration that is parallel to the ramp, angle. And then once you find that time using kinematics for the ball to slide down the ramp, then you can use that same time plugged into the acceleration or kinematics for the mass using the acceleration that you found at the free body diagram, and then find out how far it goes. That means you needed forces and you needed kinematics, and there's a lot of steps. But that you can skip all that if you're only interested in displacement. Now here's the thing, right? This approach is only useful for finding velocities and displacements. It doesn't give you time at all, right? We have no way of solving for the time other than saying that it's equal and canceling it out. We cannot solve for it. So it has its limitations, but if you're only interested in the displacement of the ramp and you're given the displacement of the ball, using this approach of the velocity center mass is super fast. All right, let's do our last two examples. These are examples that involve basically a continuous object, first of all, a solid object, so continuous mass distribution, and in a couple of cases involve a non-constant or a non-uniform density, okay? And we'll see what that means. All right, so let's start here. This is a big idea. So a thin rod of mass m, so big total m, and length L has a uniform linear density. So uniform linear density is represented by the letter lambda, and it's just mass over L. All right, so this is what a uniform linear density function looks like. Okay, it's linear. All right, so where is the center of mass of the rod located along the x-axis? Okay, so how do we go about that? Well, here's the idea, right? So this is the dm that showed up with the definition of the center of mass for continuous objects, and we're going to replace dm with lambda dx. Okay, how would we do that? Well, think about it. Dm has units of kilograms, so if I replace it with lambda dx, all right, that means I'm replacing it with something that has units of kilograms per meter times meters. All right, so I'm left with just kilograms, which I should be because it's a mass element. Okay, so it's totally fine to do this. A mass element is equal to a density function times a area or a distance element. And you can do this in 3 dimensions, and say, have something like dv equals rho, and then maybe like dr or something, okay? But in this case, it's nice, it's just single dimension, all right? So mass element is just linear density times length, but infinitesimally small length, okay? So hopefully that makes sense. All right, so here's the approach. We're just going to use the definition of center mass, x column equals 1 over total mass, the integral x dm. Then we're going to first step every time. We replace dm with lambda dx, okay? Because we can't do anything with dm. Remember, it's not useful for actually solving anything. But now look, now we have an x and a dx, right? That means we're actually going to be able to integrate this in terms of, otherwise we have a variable and a differential that match up. It's actually solvable, all right? And then we're going to make it a definite integral because we're going to integrate from one into the other. And since we have a uniform density, at least in part A, part B, you'll see we will not. But in part A, I'm just going to be able to replace that density function, lambda, with m over L. And the great thing with this being uniform is both m and L are not functions of x, so they're going to come right out of the integral, freebie, okay? All right, so there we go. Lambda is not a function of x, and that is always true of uniform density, okay? Okay, and so look at that. I went ahead and pulled m over L out of the integral. There it is. The m's cancel, okay? They would have canceled inside of the integral. Now I'm going to set this up as a definite integral from 0 to L. L is the overall length of the rod, okay? And then go ahead and solve the integral. All right, when I do the rules of antiderivatives for x, it just becomes x squared over 2. All right, evaluate the limits. And there we go. So then this is going to become, just because obviously the lower limits, that doesn't do anything, so it's just L squared over 2. That means I have an L that cancels, and I end up with L over 2. But I sure should have, right? Because, if I got any other answer, then something would have gone wrong. Because a uniform density rod, of course, has its center of mass exactly in the middle. It's got its center its center of mass at its geometric center because it's got equal mass on both sides. Okay? Okay. Now, what if it doesn't? What if this rod varies in density? All right, so in part B, if instead the rod has a linear density that varies with length from some initial value, lambda equals lambda naught, at the left side, so over here, over to the other side, the far side, the right side, with twice that, okay? So it becomes twice as dense. So it gradually, linearly becomes twice as dense. Over here it's lambda naught, over here it's 2 lambda naught, okay? All right, then where is the center of mass of the rod located? Okay, so that means that we need a function for lambda that's dependent on x that matches this idea of starting at lambda naught and ending at 2 lambda naught and gradually increasing to that rate. Okay, so we need a function, all right, and this function is going to be a lambda as a function of x, right? So obviously it's not going to be able to be pulled out of the integral, and it's going to be lambda naught times 1 plus x over L. And where do you get this formula? You get it from simply using the equation of a line, right? Because consider, I have some graph, which is lambda as a function of x. I know that there is an intercept lambda naught. I know at an x value of L, I have another value, which is 2 lambda naught, and I just need to find the equation of this line. Well, I can just use the point intercept method of finding the equation of a line, and I get that. Easy breezy, okay? All right, so this doesn't just come from nowhere. It just comes from the point intercept method of finding the equation of a line, which you've seen before, but you might be rusty on. Okay, so let's continue on. Okay, so notice this time we need 2 integrals. Okay, anytime you have a non-constant or a non-uniform density, you need 2 integrals. You need an integral, which is actually the x center of mass integral, but you also need a total mass integral, because you don't know what the total mass is. The total mass is dependent on lambda. Right? It's dependent on how much what the density is, and we don't have a numerical value for lambda, and nor do we need one. But once we find the total mass, then we'll be able to cancel out the effect of lambda naught. So in other words, we need to cancel out lambda naught from our equation, because notice it does show up in our function, but we have to get rid of it. Now, one way I could have gotten rid of it is actually giving it to you numerically, but we don't need it numerically because we can just set up this total mass integral, all right? Let me show you how that works, okay? So here is just the definition of the center mass for continuous objects. We do our substitution with the mass element, replacing it with lambda dx. We do that every time. All right, now this time we're going to replace lambda with its function. Okay, so a bit more complicated, right? But still an easy integral to solve. It's just simple polynomials. All right, and so I go ahead and split into two integrals. I got an x squared integral when I distribute the x. All right, and then this one over here I just have an x integral. All right, and then go ahead and do the rules of antiderivatives. Remember, it's a definite integral, so I'm just going to evaluate it as two limits. All right, and obviously the x squared became x cubed over 3, and then the x became x squared over 2. All right, I pulled out all the constants, which were lambda naught and m, and there we get our answer. Okay, that's our answer from our definition of the center mass. But this is not the end. Okay, you're not done because you can't give me an answer for the center mass, which is dependent on some unknown initial density. Okay, you have this answer has to be some fraction of L. There's two things wrong with it. First of all, it's proportional to L squared, so that tells me I'm not done, and the fact that I still have an unknown, as I said, initial density. Okay, so that's where the second integral comes in. All right. So since the center mass xcom needs to be in terms of L only, literally, it's just going to be L times some number, we need m in terms of lambda naught and L, okay, in terms of the initial linear density and the total length. Okay, so where do we get that from? Well, we get it from the total mass integral, all right, because that's just m, which is just differentiating over those little mass elements, obviously, right? Because we're just summing up an infinite number of infinitesimally small mass elements. We replace dm with lambda dx, just like we would have here. The only difference is there's no x, right? Okay, and same limits of integration. And then we're going to put in the function of lambda, okay? And then just continue on, go ahead and solve this. This is also has two terms, right? In this case, we had a constant that became linear. And then plug in our limits, and we get 3/2 lambda naught times L, okay? And then I just want to replace, so what I'm going to do is then I'm just going to solve for lambda naught. Okay, and there's two things I could do. I could actually take this m and substitute it in, ready to go. Another thing I do is solve for lambda naught and substitute that in. Either way, it's get the same. I actually don't remember which one I did. Oh, I went ahead and substituted in the m. All right, and so I just said, okay, well this is m, and I'm just going to replace m right here. Okay, and so then I just replace m with 3/2 lambda naught L. That cancels out my lambda naught, cancels out one of my L's. All right, and obviously the m is gone because it was substituted out. And there we go, 5/9 L. Does that answer make sense? Yes, because 5/9 is greater than 1/2. That means that the center of mass is pulled a little bit towards the denser end, as it should be. Okay, let's do it one more time, but this time for a cone. Find the center of mass of a cone of uniform density. So this time it's uniform density, but cones get thicker. So even though the density is uniform, there's still more mass at the thicker end. All right, so how are we going to do it? Okay, so we're going to have the total mass, m, this is the mass of the whole cone. Our little mass elements are going to be rho dv. In this case, they're rho instead of lambda because they're actually three-dimensional. It's like an actual disk. So the rho represents volumetric density. dv is a volume element instead of a mass element. All right, and also instead of dx, right? Because before it was a length element, if you will, or just an infinitesimal small piece of length, or you could just call dx the x differential, whatever you want to call it. Okay. So we're going to use the definition of the center mass for a solid continuous object. In this case, we'll do it in the z-axis because that's what we're asked for. All right, that's the only one that won't be, because everything else cancels out. So the x center mass and the y center mass are both going to be 0, right? Because everything's symmetric. The only thing that's not going to be 0 is the z center mass. All right, and there is going to be 1 over total mass z times dm. All right, and then we're going to have our total mass integral. Okay, and dm is the mass element. Just a good reminder there. All right, here's the thing: we actually don't care about this one. Right? Now, I put it up there because maybe you think we'll need it, but we don't. And we don't because rho is constant. Now, we could have a non-uniform density cone. We could actually easily deal with that because then we could just have one extra step. But in this step, because it's uniform density, we don't care about this one. Okay? All right? So we're going to go ahead and set this up. So we're just going to have our dm. We're going to replace it with rho dv. Okay. But the problem is that rho dv is still, the thing that is different about the cone as opposed to the rod is that, obviously it's not one-dimensional anymore. So although we don't have to worry about this total mass integral, we have to worry about something that we didn't for the rod. And that's the fact that we're still not done with our differentials. Our first substitution from dm to, rho dv, it's not enough. It was enough in the case of going from dm to lambda dx because then we would, we had dx and we had x, right? But here we don't. We got z and dv. They're not the same. So what do we need to do? Okay, let's see. So first of all, we need to acknowledge that rho is the density of the cone, which is just m over v. And that's true because it's uniform density. All right? So that's great. Uniform density, that wouldn't be the case, hence we would need the second integral, okay? But we don't this time. Wonderful. Okay, so that means our rho is just going to come right out of the integral because they're constants. But now the dv, okay? The dv is what we maybe worry about, or just what we need to deal with, okay? All right, so here we got, replace the rho. Rho, by the way, is just volumetric density, and it's spelled like this, rho, it's a Greek letter. All right, so we got our mv, pulls out, the m's cancel, so we just have a 1 over v outside the integral, and notice what I do now. I replace the dv with pi r squared dz, okay? Where did that come from? All right, well, that comes from the fact that the volume of the of each little volume thing, each infinitesimally small amount of volume, right? Because dv is a volume element. It's an infinitesimally small piece of volume, and it's infinitesimal because the thickness is infinitesimally small, right? It's dz in thickness, but it doesn't have a well-defined cross-sectional area. So all I have here is the area of a circle times that infinitesimal thickness. This is a cylinder. It's an infinitesimally thin cylinder, but with a well-defined surface area, okay? But what is r, okay? Because we're still not quite done here. We got the z and the dz, so we're so close, but we're still stuck with an r, and r is not a constant. Because think about it, r is the diameter, or excuse me, the radius of our cylinder here, which is the cylinder, which is the volume element. But r changes, right? So I mean, if I was looking at, you know, little volume elements down here, because I'm summing up an infinite number of them, well, obviously r would be less. And when I'm summing up the very last volume elements up at the top to finish off the cone, r would be bigger. So r changes. R has a functional dependence on z. But since it's a cone, that functional dependence is linear. So r is just r over h times z, right? See it? Okay. So that means, and by the way, that because r equals 0 when z equals 0, and r equals h when z equals h, right? And this clearly satisfies that. And again, you could find this from just the equation of a line. This is, again, a point intercept, but in here the intercept is the origin. Okay, so it's very, very similar to finding the linear function, the linear density function that we did in the last example, just using the point intercept method of finding the equation of a line, but it's even easier this time. Okay, so it's just r equals r over h, the total radius. Okay, that's the up here. Or the base radius of the cone, the height of the cone, and then z. Okay? All right. So then we're going to substitute that in. So then r substitute in with this expression and square it. And what's the beauty here? R is a constant, h is a constant. Now we have a z squared, and we got a z, and we got a dz. We can solve our integral. All right? So I pull out all the constants, the pi, the r squared, and the h squared. I leave the z cubed that's inside. I'm going to make it a definite integral from 0 to h. All right? And I wait to make it a definite integral until I've done all my appropriate substitutions. Okay? All right, and then we just go ahead and solve it. All right, I'm going to go ahead and plug in the volume of a cone. That way I'll cancel out a lot of my constants. The volume of a cone, you look it up, all right? Or I guess you could solve it using calculus, but in this case I just looked it up. The volume of a cone is pi r squared h over 3. Okay, this is a well-known volume formula. All right, we'll put that in for v. All right, and then we just cancel out everything. Pi's cancel, r squareds cancel. All right, h's don't cancel yet because we're going to have an appropriate power of h show up when we solve our derivative. Or excuse me, our integral, which is the antiderivative, right? So my z cubed became z to the 4th over 4 when I did the rules of antiderivatives for polynomials. Evaluate it from 0 to h. All right, and there we go, right? So then this is after the cancellations of substituting in the volume of the cone in here. And so then I just end up with 3. I got an h cubed left over because the h times h squared. And then I got an h to the 4th up here. All right, so then I have a cube cancel. So I'm only left with an h in the denominator. So what do I get? 3/4 h. All right, so the z component of the center of mass of the cone, remember the x components and the y components are both 0, but the z component of the center of mass of the cone is 3/4 the way up. Somewhere right around there. All right, pretty cool, right? Pretty cool. And the approach, you know, it's a bit to take in on first pass, but it's all the idea is that we need to solve an integral, the same integral every time, and we just always have to do substitutions, sometimes more than other times, in terms of getting rid of the dm and actually having an integral we can solve. All right. Well, thank you so much for watching this video on the center of mass. We covered a couple ideas and finished up with the most complex ones. I hope it's been interesting and informative.